Welcome to my channel Maithili SK. In this session, I'm going to explain you about angle modulation, representation of the same, that is frequency modulation and PM signals. To start with the session, I'll give the introduction about the angle modulation, difference between AM and FM. So we have studied about amplitude modulation in the previous case. Now it is angle modulation. So we'll see the difference between amplitude modulation and FM. It's a very important question as far as university is considered. And the mathematical representation of the frequency modulated signal, types of FM, and we'll see the conversion factor, how we'll get FM from PM and vice versa. Start with the angle modulation. So what is angle modulation? The angle, the meaning itself is nothing but which is related with the phase changes or the frequency changes. So angle modulation is the process in which the frequency or phase of the carrier signal is varied in accordance with the message signal. The standard equation of this angle modulated signal is dependent on this both the frequency as well as the phase change. Hence, it is simply represented as S of t as Vc sine omega t plus phase change, that is phase angle. So it can be simply represented as Vc sine of phi, where this phi is nothing but the phase angle of the carrier. So from the previous amplitude modulation case itself, we know the output can be all represented in terms of carrier signal. This is the carrier voltage, and the sinusoidal or cosine signal is taken with respect to the angular frequency, that is omega c of t plus angle, that is instantaneous phase deviation. So altogether this can be represented as the phase angle of the carrier signal. So as per the equation and definition, the change in carrier frequency involves change in phase also. So with respect to this equation case where we have mentioned, this is the equation. So the change in frequency also involves change in phase. Hence, the direct FM modulation causes indirect phase modulation and vice versa. So finally, the relation will be revealed at the end of the session. What are the types of angle modulation? So types of angle modulation involves, as we are directly involved with frequency and phase, hence it is divided in two cases of frequency modulation and phase modulation. So general definition of a frequency modulation and phase modulation is given here. It's nothing but the process by which the frequency of the carrier wave is instantaneously varied with respect to the message signal. As well as for the phase modulation case, the phase of the carrier is instantaneously varied with respect to the input message signal. What are the important terms used in frequency modulation is explained here. It involves with frequency deviation. Since there is a change in frequency, the frequency deviation part is represented as theta of t. It is the change in frequency of the carrier we can simply define, and it is defined as the first time derivative of the instantaneous phase change. So it can also be represented as derivative means d theta of t by dt. That is also a frequency deviation. Sometimes in books, some other cases they will be representing in terms of delta also. Next important term you have to involved in frequency modulation is deviation sensitivity, which is represented by a factor called as k in k suffix fn. So it provides the relationship between the output parameter change in respect to the input parameter change for the frequency modulation case. So it is nothing but the ratio of change in the output frequency to the change in the input voltage. So change is represented by delta, and frequency is represented with respect to omega term, that is 2 pi f term by Vm. Next term we are using in frequency modulation is the bandwidth. Here the bandwidth plays a major role, where it is not simply adding the signals or sidebands present here. Since there are no more number of sidebands are present in case of frequency modulation, we will be dealing with a rule called as Carson's rule. So Carson's rule states that the bandwidth of an FM wave is twice the sum of the frequency deviation and the highest modulation signal. So you can say it is given mathematically as twice the sum of the change in frequency with the highest message signal frequency. So it is 2 of del f by fm in hertz. Next is an important term. There is a modulation index referred for frequency. It is denoted by mf. It is nothing but k into Vm divided by omega m. So we know k is nothing but a constant term. Vm is nothing but the message signal voltage, signal voltage, and omega is nothing but angular frequency term with respect to message again. So what is mathematical representation of frequency modulation? We'll derive the equation for Fm now. So first write down the definition for frequency modulation here, and we'll start with the representation of message and carrier signal. Since we know modulation is dealing with carrier as well as message, so I am going to represent the message signal as Vm cos omega mt, and carrier signal here is represented as Vc sin omega ct with respect to a phase change of theta. Since this carrier is phase shifted, we are representing in terms of theta, that is instantaneous phase deviation is also involved here. So S of t is nothing but that is here instead of frequency terms, all these terms represented denote omega is nothing but the angular frequency, Vc is the carrier frequency, and theta is the instantaneous phase deviation. And as a whole, this can also be represented as a phase change of the carrier signal. So next case, we are going to represent the same Vc of t with respect to a phase change, Vc sine of phi. So what is this phi is nothing but already we have mentioned instead of that phi this is nothing but the earlier equation has sine of omega ct plus theta. So here just I have replaced this by phase change of phi. So to find the angular velocity, we have to differentiate the equation number 3. Equation number 3 gives the phase change with respect to time, that is d phi by dt. So here we are having only the time dependent factor with omega c, and this is not time dependent, so it is 0. So we just get omega c term alone. So frequency after modulation by definition is given by, so it is nothing but instantaneously we are getting an output. So omega I is nothing but omega c respect to message signal k Vm of t. So omega c is carrier signal 2 pi fc, and here this is with respect to the message signal Vm of t. Now we know what is our message signal. We have assumed in terms this Vm cos omega mt. Just to substitute that from previous first equation. So this is our first equation. This is the message signal Vm of t. So I am going to substitute here Vm of t over here. So it becomes omega I is nothing but omega c plus k into Vm cos omega mt. This becomes equation number 6. So k is represented as a proportionality constant. Now to find the instantaneous phase angle of the modulated signal, we have to integrate this. So again arriving back here, instead of differentiation, if you integrate it, we will be getting the signal phi. So now that is done here by integrating the same equation. So phi of t is integrated with respect to omega I of t term. So we here, this is the term we are representing. So we are going to substitute here with respect to omega it. So substituting omega I term from the previous equation, we will be getting omega c plus k into Vm of t cos omega t dt. So substituting from the previous sixth equation, substituting 6 in 7, this equation becomes this. So now integrating, we will be getting omega c into t. This term it is k into Vm. For this term, if you integrate, it will be sin omega mt by omega m. So this omega m is taken as constant, so it is taken outside, plus a angle term, that is theta 1. So theta 1 will be the integration constant, and this can be neglected since it has no role in the modulation process. Now the instantaneous amplitude of the modulating signal is given by output, that is message signal Vfm of t with respect to Vm sine of omega Ct plus this term of omega I, that is plus k into Vm omega m into sine omega mt. So hence this equation 10 is the mathematical representation of the frequency modulated signal. So we know the modulation index we have represented in the previous. So this k into Vm into omega m is taken from the mathematical derivation part. How it is obtained? This is the modulation induction part. So it is simply, it can also be given as Vm sine omega Ct plus Mf into sine omega Mt, where Mf gives your modulation index. So equation 10 gives the mathematical representation of Fr. Now coming to the phase modulation. Phase modulation is simple by definition. So here also we are considering definition for the phase modulation. Sorry, this must be phase. Phase modulation is a process by which phase of the carrier is instantaneously varied with respect to the message signal. Considering the message signal part as Vm cos omega mt and Vc of t as such, this is the actual phase change we are happening, the instantaneous phase deviation. That's why it is given in bold representation, Vc sine of omega Ct plus theta. Now coming to the representation part, the phase change is represented in terms of theta, that is nothing but instead of Fm factor, here I am taking it as Kpm into Vm of theta. So here Kpm, here Vm of t we know from equation number 1. So substitute that from 1. So it becomes Vm cos omega mt. So it becomes K into Pm Vm suffix cos omega m theta. What is this K into Pm is nothing but the deviation sensitivity with respect to the phase. Simply it can also be called as phase deviation sensitivity. So after phase modulation, as per definition, the instantaneous voltage will be V suffix Pm of t in terms of Vc sin omega Ct with respect to theta. With respect to this change, we are going to add the signal. So here, instead of this theta, substitute this equation what we have obtained for 4 in 5. So it becomes sin of omega Ct plus the phase deviation sensitivity involved equation. That is, this is replaced now by the phase modulation index of the phase modulation, that is k into Pm into V is represented in terms of Mp simply. As we have represented Mf in the previous case, this is represented in Mp term for the phase modulation case. So equation 6 gives the phase modulation representation in the mathematical format. So now we'll see the difference between a amplitude version modulation and the frequency modulated version. So with respect to definition, we know here the amplitude of the carrier is only varied with respect to the message signal. Here frequency of the carrier is varied with respect to the message signal. And the modulation index part is defined as the ratio of voltage of the message signal to respect to the carrier signal voltage. Here it is nothing but a constant factor involved with respect to change in the message signal voltage with respect to the angular modulating frequency. So it is K into Vm by omega m. And it has three terms, that is carrier, lower sideband and upper sideband. But it has only one carrier with the more number of sidebands with respect to the equation what we have arrived. And it here it is lower efficiency because its efficiency turns out due to the number of sidebands is very less, so more number of message signal cannot be transmitted. But here there will be more efficiency since there are infinite number of sidebands to carry the message signal. Here the noise interference is much higher, whereas here the noise interference is low. And the amplitude modulation of AM depends on the modulation index, and hence the transmitted power is varied in accordance with the modulation index. The equation itself we have seen with respect to modulation index. So the transmitted power is varied in calculation of PT term. But here for the frequency modulation, the amplitude of FM is independent of the modulation index and the transmitted power will become constant here. So modulation index should be always less than 1 for a perfect modulation process. But here there is no limitation for the case of modulation index. And it is amplitude modulation case, it is used in medium frequency and high frequency ranges, whereas here it is used to broadcast at high range of very high frequency range and ultra high frequency range. And adjacent channel interference is more, so that's why the noise is more here, and adjacent channel interference is very low, so the noise interference is low. It is very simple to generate and transmission, whereas it has more complexity in generation and transmission because of the more number of sidebands present. So if it is asked in a 13 mark question, or it can be asked as a short notes also, a 6 mark question, you could at least write 6 to 8 points for a 6 marks, and for 10 marks all these points is very important for a university question. Coming to the types of frequency modulation is divided into two types as narrowband FM and wideband FM based on the modulation index. Here modulation index is always greater than 1 and a minimum value will be always 5 in narrowband case. Whereas for a wideband case it will be always less than 1, that is modulation index is always less than. And here the frequency deviation will be 75 kilohertz, whereas here the frequency deviation will be 5 kilohertz. And the modulating frequency range is 30 hertz to 15 kilohertz in case of narrowband FM, whereas the modulating frequency range is up to 3 kilohertz in case of wideband FM. And here the bandwidth is 15 times of the narrowband FM, whereas the bandwidth is only twice that of the message signal frequency. Here the suppression of noise is more in case of narrowband FM, whereas suppression of noise is very less in wideband FM. And narrowband case it is used in entertainment and broadcasting range, whereas wideband FM it is used in mobile communication. Now coming to the conversion part with respect to FM and PM. As we know, this FM and PM is indirectly involved with respect to modulation part. So we can either get FM and PM in an indirect way. So one of the method here is by involving a differentiator and integrator. In how we are involving the differentiator and integrator with respect to the generation part is seen here. So conversion of FM to PM. So we are going to use a frequency modulator's case, then a frequency modulator case to generate an PM signal from an FM signal. So PM wave can be obtained from an FM wave by differentiating. So by differentiating the modulating signal before applying it to the frequency modulator. So we are using a differentiator and a frequency modulator to produce an PM wave, whereas in the second case we will be generating an FM wave by means of using a phase modulator case just by integrating the message signal. So a message signal is integrated to produce an output of an integrated message signal, and that message signal is passed to the phase modulator, means with the help of a local oscillator signal to modulation, that is a carrier signal is given here to produce an FM signal. So it's a very important 2 marks question, how we will convert or how we will get FM from PM and PM from FM. Hope you understood today's topic of angle modulation, introduction part, generation of these signals, etc. So now we'll see the spectral characteristics of angle modulated signal in the upcoming session. So the important questions what they are asking here in FM generation here is, first one will be the mathematical equation or derivation of FM and conversion part of FM and PM short notes. And 2 marks difference between this AM and PM is asked, AM and FM is asked, as well as FM and PM is asked, and the conversion of this PM to FM block diagram is asked. This general block diagram is asked in angle modulation signal. Hope you understood today's topic. We will see the next topic of spectral characteristics of this, both frequency and phase modulation in the upcoming classes. Thank you.